Hello, and welcome to today's webcast brought to you by Industrial Laser Solutions. Today's event, Right and Wrong Ways to Manage Laser System Variables in Material Processing, will be presented by John McCauley, Product Specialist for Ophir Spiricon. This presentation is both live and interactive, so you can ask questions at any time by clicking on the Ask a Question button in the presentation window. If you're running pop-up blocking software, you will want to disable it to view this webcast. In addition, we recommend that you close down all other applications for better performance. For your convenience, this presentation will be available on demand within 24 hours of this live event. A reminder email message will be sent to all registrants with a link to the archive. It will also be accessible from our homepage at www.industrial-lasers.com. Now, it gives me great pleasure to introduce today's speaker, John McCauley.
Thank you so much for the introduction, Jonelle. I want to, first of all, thank Industrial Laser Solutions for the opportunity to talk, to connect with laser users, and for the opportunity to help laser users. And whenever I get an opportunity like this, I'm always very grateful, so I certainly want to thank you for the opportunity. And also want to thank everybody who is participating in listening into the webinar. It really does say something about you as a person, as a laser user, to take time out of your no doubt busy day to get information. And it's my goal and my promise to you that I'll do my very best in providing you with information that is helpful to you, and some tips and techniques that you can use and take away and apply to your everyday life as a laser user. So thank you so much. So go here. There we go. So why are we holding this webinar today? Now, chances are you're here today for one of several reasons, or one of many reasons. Chances are you're here today because you're someone who uses lasers. Okay, well that's pretty much a given. Industrial Laser Solutions, typically they don't speak to too many other people besides people who are using lasers. So that's probably a safe assumption. Chances are you're here today because you want to understand the performance of your laser better than you do now. I think that's pretty safe to say. Otherwise, you probably have, you've got 100 other things you could be doing, but you're here today to learn how to better understand your laser. You might be here today because you're someone who's having or have had problems with their laser. Now, if you have worked with lasers for any significant amount of time, you probably have run into problems that you need maybe some help understanding how your laser is performing so that you can solve those problems. I don't know everybody's story here, but chances are that might be the case for you. Chances are you're here today because you're familiar with or you have heard about laser measurement, but maybe you don't know how to use the data that laser measurement techniques provided. And once you gather that data, how do you apply the data that it provides? I don't know your story, but chances are you might be in that category. Perhaps I'm going to add this part. Perhaps you've spent more time than you needed to in application development. If you have not used the laser measurement techniques, perhaps you've spent more time than you've needed to troubleshooting problems that you've had with your laser. But in general, perhaps you spent more time than you've needed to trying to understand your laser. These are all questions that any laser user is going to have at some point. So it is really my goal with this webinar and partnering with Industrial Laser Solutions on this, and try to help you understand your laser system better than you have in the past. What we're going to discuss today in this webinar, Laser Measurement Best Practices, we're going to discuss the challenges that come with laser material processing. So you got a laser, you want to use it to do something with in application to a material, all right? So we're going to talk about the challenges that come with that, And I'll be honest with you, most of the information is going to be geared more towards the additional challenges that you might have if you're using a high-powered laser for material processing. But the concepts and the general principles that I'll talk about are really true with any laser that you're using. I'm going to talk about important laser parameters to measure, so what you should be measuring on your laser and why you should be measuring those performance parameters. I'm going to talk a little bit about the different laser measurement techniques. There are some legacy ways of collecting information on your laser, and there are also some modern-day laser measurement techniques. I'm going to talk about the pros and cons of each mindset, but I'm going to mainly talk about the differences between legacy and modern-day laser measurement techniques. I'm going to talk about laser source parameters and laser system parameters. Now, what's the difference? We're going to talk about the difference between these two sets of measurements, and then which ones should be applied and when they should be applied. And then finally, when we're talking about tying it all together, when we're talking about the real application of all this knowledge or the wisdom that I'm going to be giving to you, I've got 3 case studies that I'd like to present at the end of the webinar where laser characteristic measurements really did make a difference in these particular lives of these laser users. Okay, so chances are if you're using a laser for material processing, you are already familiar with the term power density or energy density as it applies to pulsed lasers. But in the event that you aren't, I'm just going to real briefly talk about the concept of power density because I am going to be referring to it quite a bit during the webinar. In the layman's term for power density is really the measure of how the laser is applied to the material that is being processed. And that's a very simple explanation of what power density is. It's a term that's expressed in watts per centimeter squared, okay? So the top of the formula is the W, okay? It's the watts. Now, what is watts? Watt is the laser power, or it's the measurement of the laser power, the amount of laser that's being applied. The bottom of the formula is centimeter squared. This is a unit of area. So it represents the beam size that's being applied to the material being processed. So you've got how much laser, and then you've got how big of laser being applied. And both of these laser characteristics are very important to measure and to understand in material processing. The bottom of the formula is also known as the spot size, the beam waste. There are some other terms that are used to define this particular part of the laser, but those are really the 2 most important terms. So what happens to power density when one of these parameters changes? It really is very important to understand when one of these bits of the formula changes, how does that affect how the laser is being applied to the material being processed? So for example, if there's a gradual decrease in laser power, what's that going to do to the formula? It's going to decrease the numerator, the top. So it makes sense that the overall power density is going to decrease when your laser power decreases over time. So, and also if you have any fluctuation in the spot size or the location, what's that going to do to power density? It's going to affect the denominator. So if you have any changes, so if, for instance, if your spot size is decreasing over time, it makes sense that if your spot size is increasing over time, it's going to make sense that the overall power density is going to decrease over time. But any changes, what I want you to walk away with is any changes in your laser system, and you will have them, any changes are going to change the way that the laser is being applied to your material, okay? Let's talk specifically about some challenges working with high-power lasers. I first want to start off by saying that regardless of the high-powered laser that you are using for material processing, the laser quality has greatly increased over the years. I really do want to commend the laser OEMs for really digging into some of the problems in laser efficiency that there have been over the years, and they're really providing great products to their end users. So some of these problems have been cost of ownership. It's greatly decreased over time. Wall plug efficiency, how efficient the laser source is, that's greatly increased over time. and the amount of maintenance that you have to do to your laser system, that has greatly decreased over time. So I really want to commend not only people who provide laser sources, but also people who integrate laser sources into a complete system. But that doesn't change the fact that lasers are still made of physical matter, okay? They're always going to be made of stuff, all right? And stuff is going to degrade over time, regardless of what kind of laser system that you have. Components are going to get dirty for whatever reason during maintenance or during failure of systems. Laser system components and sources are going to catastrophically fail from. So the bottom line is, as a result, you're going to see, because, regardless of how well the laser source is, it's still made of physical matter, and as a result, performance of your laser system, your overall laser system, is going to drift for one reason or another. So a lot of times I talk with customers and I say, well, what happens when your power decreases? Well, they say, well, we ramp up the power. Okay, ramp it up and keep going, right? So in my opinion, that's not really a correct approach of applying that laser parameter measurement. It's just to ramp it up and keep going. In the short term, that's maybe a good solution. It's going to be a very quick solution, but the bottom line is, when you keep ramping your laser system up, you're not addressing the problem that you have with the laser system. There are going to be changes in spot size over time. It's just a fact of the matter. There is going to be, because of thermal effects on your laser system, there will be a drift in the focus spot location. Now, we're talking about material processing, so we need to understand how the laser is being applied to the laser system, okay? So any changes in power, any changes in spot size is going to be a result in a change of how your laser is being applied to the material. Okay. If you don't take a proactive approach to measuring and understanding your laser, the bottom line is there's going to be much time spent recovering from that. There's going to be a lot of money lost, both in scrap and labor costs, being sucked into trying to understand why the laser is performing so bad. So that's really why, number one, it is important to measure and understand your laser source and your laser system, and that's really why we're having this webinar, so that we can educate on how to do that. Okay, so let's talk about some meaningful laser parameter measurements. So what do you need to measure on your laser? Okay, so output, power, or energy. And I think probably everybody here is probably very familiar with how to measure power or energy on your laser system and what that measurement means. When you're talking about power, you're talking about continuous wave power of your continuous wave laser source, or you're talking about average power if you do have a pulsed laser. Energy, of course, is measuring the energy per pulse from your pulse laser. Next is your spatial profile, what's commonly known as the beam profile. Beam profiling, you probably have heard that term as well, but that's where you are measuring. You're actually measuring the beam size or the spot size. You're measuring the beam shape. You're measuring the beam roundness, a fit to a Gaussian or a fit to a top hat, things like that are what you're going to be measuring when you measure a beam profile. Again, when we're talking about laser material processing, these are the two measurements that you're going to take in order to fully understand how the laser is being applied to the material being processed. Okay, this is going to give you your two bits of information, your watts per centimeter squared. There's also caustic measurements, so measurement of the M squared or the beam parameter product. In general, what this measurement is going to give you is an overall quality measurement of your not only your laser source, but your laser system as well. It basically tells you how focusable your beam is to the material being processed, but it is an overall, it's a laser quality measurement. The laser spot location. So in addition to the beam profiling information that measures your spot size, there are also devices out there that measure the spot size and the location. So if you do have any drift in your focus spot, either up or down, depending on what optics you're using to focus the beam, There are devices out there that will actually measure the focus spot location dynamically, so it'll tell you how, what the spot size location is. And then finally, when you're working with pulse lasers, it is really very important to measure the temporal profile or the pulse shape or the pulse duration. So not only how long you have for a pulse, which should coincide with what, the input parameter that you put on your laser source, but what the shape of that particular pulse is. So these are really all the laser parameters that we recommend you measuring on your laser source. Let's talk a little bit about legacy laser measurement technologies. Now, these technologies have been around for 20 plus years, and they really have served us very well. When you're talking about laser power measurement, here's one way to measure the laser power. It's known as what we refer to as a power puck. You fire the laser into that hunk of metal there, and it's going to give you a number of how well your laser is performing at that time. When you're talking about beam profiling, there are several different techniques. One is pictured here. It's the acrylic mode burn. You fire the laser into this block of acrylic. It gives you, beam shape and beam size information. Same thing with burn paper. You fire the laser at this burn paper for a split second. It's going to tell you the beam size, beam shape. Mode place is another dynamic way of measuring your laser mode. You fire the laser at that phosphor plate. You illuminate it, and it gives you a dynamic view of your laser source. There are some drawbacks to doing it by these methods. They are cheap. I'll give you that. They're very inexpensive. They do give you some information about your laser, but ultimately it's going to be subjective information that's going to be provided to you. So you fire it into this acrylic mode burn. One guy's going to look at it and say, hey, it's great. The next guy's going to look at it and say, I think we got some problems. It's a subjective interpretation. Most cases, you're going to get a single data point. So you fire the laser at this acrylic mode block, you get a data point. You fire it at the power puck, you get a number. It's really not painting a very complete analysis of what is going on with your laser system dynamically. If you've worked with lasers, you know that from the beam on time, you get one characteristic, and then several seconds later, you may have a very different set of characteristics as far as how your laser is performing. And again, we're talking about material processing. So when you're gathering this data about your laser, what kind of information do you want? Do you want single data points? Do you want a number for watt? Do you want a number for beam size? I might make the argument that you want to paint a more complete picture of the analysis of your laser, which brings us to modern day laser measurement techniques. When we're talking about laser power or energy measurement, electronic laser power energy measurement is really going to be the way to paint the most complete picture of how your laser is performing. So not only at the beam on time, but several seconds or even several minutes after your laser is on, there might be some changes between those 2 points in time. And electronic data measurement is really going to be the way to give you that information. Same thing with beam profiling. Most of you are familiar with camera-based beam profiling, scanning slit technologies. These are both ways to get spot size, spot shape information dynamically. So again, if you have any changes in your spot size, your beam waist, these are really the ways to give you that information as far as dynamic changes over time. There's another device that uses Rayleigh scattering as a technique of data acquisition. It actually views the caustic of the beam where the power density is relatively high. You get Rayleigh scattering off that laser beam, and it gives you spot size location. It gives you spot size measurement, spot location measurement, in addition to your beam quality measurements such as M squared and beam parameter product. These are really the techniques that are, number one, it's going to give you industry standard analysis. So all of these the electronic power energy measurement, it is mistraceable. It gives you a calibrated result. When you're talking about camera-based or scanning slit or even Rayleigh scattering techniques for beam profiling collection, it does give you ISO standards as far as the data acquisition. So it's industry standard analysis. So I'll argue that it gives you a more objective analysis of your laser. It gives you immediate live data acquisition. So as soon as you turn your laser on, that laser on time, included with how your laser changes over time, it's going to give you that analysis. So in general, it's going to give you a more comprehensive analysis of your laser beam. Again, we're talking about material processing. So dynamic changes in power, dynamic changes in beam size. This is really going to give you a more complete picture of how your laser is being applied to the material that you're processing. Okay, so there really, in general, there are two modern-day laser measurement approaches. One is what we call the in-process measurement. You see this diagram to the right. You've got a laser system. It's going through a mirror. It's going through some beam shaping optics. And then it's before the process, it's splitting off the laser beam. It's going into a camera there for the data acquisition. Okay, so that's what we refer to as in-process measurement. And then there's a technique that we refer to as at-process measurement. So I don't know if you can tell from the picture here, but the entire laser system is being analyzed. So there's a beam profiler to the right. There's a thermopile element at the bottom, and then at the bottom left, this is the device that measures the temporal pulse. So it's analyzing the entire laser system at one time. Now, there are pros and cons to each one of these approaches that I just wanted to touch on. The real pro at in-process monitoring is that you've got a continuous system measurement and analysis. If you think about it, regardless of when the laser is being applied to the material, you are getting a signal. The drawback to doing that is it really only analyzes part of the laser beam, right? So it's splitting it off before the process. So anything that happens past that is really not being analyzed. And to be honest with you, when you talk about material processing, most of the failures is going to happen at the process because of the dirt, because of because of the environment. When we talk about at-process monitoring, conversely, the complete system measurement is the complete system is going to be measured and analyzed. So you are measuring the laser as a complete system. But the drawback to doing this is that the laser must be taken out of production. So you must take the laser offline to make these measurements. Again, I encourage you to look into either one of these approaches. It really is going to give you very good data about your laser. So let's talk about a typical laser system. And again, we're really primarily focused on industrial lasers. So I've got a really crude diagram here, so bear with me there. First of all, you've got the laser source. Now, the laser source is going to be an ND YAG. It's going to be a fiber. It's going to be a direct diode, a disc, a CO2. Lots of different laser sources out there. These are just some examples. Solids, liquids, and gases. These are all used to make a laser source. And then you've got once you've got the laser light, you've got that magic that's happened. You've got to deliver that beam to something. All right. So this is usually done with free space optics. And in these systems, there's usually several free space optics directing the beam to where it needs to go. Process fibers, you can use it. You can deliver it using a fiber as well. There are going to be shutters. There's going to be apertures. There's going to be purge gas in the beam delivery system. And then finally, when you've got the laser to where you need it to go, you've got some kind of processing head that is going to be dictated by the what you're using the laser for. So there's cutting, there's welding, there's scribing. This is your laser processing head. These are made up of beam shaping optics, scanning mirrors, focusing lenses, focusing mirrors, process gas and a nozzle, protective cover glass. There's a lot going on with this laser system, and I guess what I'm getting to is this: the complete laser system is made up of stuff, and more stuff. Right? Every single time that the laser comes in contact with one of these systems, it's coming in contact with stuff. And I guess the point I want to make is this. So you might have a laser source, and you've taken a beam profile, for instance, on the laser source, and it might look like this. It might look like something that you're used to seeing, right? Nice round beam. The energy is in the middle. It's not elongated or anything. It's not off balance. It's a really nice looking beam. So it might look like this at this point. Once it goes through the stuff, once it goes through the optics, the shutters, and whatever else, it may, degrade a little bit. It may, be a little off-center. Really all it takes is one mirror to make it look like this, a little off-balance. Your energy isn't that great as far as the balance, and it's clearly off kilter there. And then finally, when it reaches the processing head, it's going to be, more stuff that you're coming in contact with. So by the time it reaches your process, it might look like this, okay? And there are a couple points that I want to make here. Number one, every single time that the laser beam comes in contact with a thing, it's got the potential of changing, okay? So every single time it hits a mirror, if the mirror is not up to snuff, it might change, right? So you can see, you can get an idea of of how complicated the laser system is, and get an idea of how many times the laser touches something. Bottom line is it's got, there really is a lot of potential for the laser touching, several systems. Okay, the other point that I want to make at this point is I get a lot of questions about, well, my laser beam profile doesn't really look that good to me, okay? And then at that point I'll ask them, well, how is the laser performing? Well, it's performing okay. It's doing, it's welding well. It's got the right power output. But that picture, at the bottom right, that really doesn't look that great to me. And usually my response, to be honest with you, is who cares? Who cares what it looks like? If you've got a laser that looks like what it looks like at the bottom right, and you're producing good parts, and you've got the correct power output, you've got the right beam size, who cares what it looks like, but keep it right there so you keep continuing to make good parts, okay? So just to clear, I only say that because I've got a lot of questions about that particular concept of looking at the beam profile and not liking what it looks like. So I'll say that. All right. So finally, I want to wrap up with 3 different case studies, and these are real life people. These are real life laser processes, and these are some ways that we, as people who provide laser measurement techniques, these are 3 ways that we have helped these individuals. First one is an application development case study. In this particular case, we have a pulsed laser welding process that consisted of 4 pulses. Okay, so that's don't care about the customer name, don't care about the industry, don't care about the laser source. Here's the application. We need 4 pulses at the material. Okay, so what was programmed looks something like this. 1 pulse that was initially high, and 3 pulses at a lower energy, okay? So you see at the left there, you see a graph over time. So you see a high energy pulse and 3 lower energy pulses, and then the corresponding beam profiles. These are what the beam profiles may have looked like, something representative of this. But the laser was not performing the way it was programmed. So that's where really we came in, is we came in with the laser performance measurement tool to try to analyze and try to troubleshoot how what was going on with this particular laser. Well, what we measured actually was a low energy pulse followed by a ramping up of each consecutive pulse. So bottom line is the laser was not performing at all like it was programmed to. And as a result, the first pulse was not penetrating, it wasn't doing its job, and then by the 4th pulse, it was actually melting through the material that was being processed. So bottom line is that the laser was not doing the job. The person developing the application before we came in was spending a lot of time trying to figure out what was going on. Quite honestly, they were spending a lot of money in scrapped material. As you know, especially with laser, with medical device application, you're running into some really eccentric metals that is very expensive. You don't want to spend a lot of time and a lot of money wasting on scrapping or trying to develop the application when you could be understanding your laser a whole lot better. So there's a lot of lost time, a lot of scrap material in the application development. Case 2 is a laser system validation story. So again, we've got a pulsed laser welding system, and what we're doing with this particular system is we're welding 2 dissimilar metals. So here's a This is not the product. This is not the customer's product. This is just a bone screw I just want to use for this example. So if you picture this bone screw made up of two different metals, you've got metal number 1 at the head, you've got metal number 2 in the screw part of it, and what the customer is trying to do is put a laser weld on these two dissimilar metals around that part. Okay? So what they did was they bought a system, and they did the application work. It went good, and they started applying the laser. They, making good parts. The parts were great. What this particular customer of mine saw was an increase in orders. So they have larger quantities of orders. They've got more customers. Everything is going great. So what they did was they actually bought an additional laser system. All right. So with that additional laser system is the same OEM, same laser system, same source, same model and everything. And what they did was they took the laser parameters that were in the first laser, and they just plugged them into the second laser, okay? Why can't you do that? They're the same laser, why not? They plug them in, they start going. Well, what they found was that this second laser system was cracking the welds, and they couldn't figure out why. So that's when my customer called me in, and we did a set of apples-to-apples laser measurements. So what we found on this particular laser system, there are 4 laser settings that they had set up. And you can see that the results of the laser measurement. So we are getting a laser power of an average power of about 20 watts. We're getting a peak power based on the beam diameter measurement of about 2.56 kilowatts per centimeter squared. We got a spot size measurement of that, and we've got a lithicity measurement, pretty nice round beam. This is a picture of the laser beam profile. It's nice and round. This is the good beam that's producing parts. Okay, so we take a set of measurements on the second laser system, and we got this. So the same parameters, right? We were getting an average power of 27 watts. We are getting a peak power or power density of almost 3 kilowatts per centimeter squared. We are actually getting a larger spot size, right? So if you think about your equation, you see how that affected the power density. We are getting an ellipticity value of about 92% instead of a nice round 99%. That's the beam profile. That's the actual beam profile that we are getting on the second laser. You see, just visually looking at the two, you can see that there is much different, two very different laser systems being applied, even though they're of the same system or same OEM and the same model number. So what we did some experimenting, and over the course of about a half hour or so, we just played around with the laser parameters. All right, we decreased the peak power, we decreased the pulse width. Those are really the two parameters that we changed. And as a result, we got something that was more in line with what the laser number 1 was producing. We got a right around 20 watts. We got right around 2.5 kilowatts per centimeter squared as far as the power density. The ellipticity was a little bit off. It's still, 87%. So that was something that they were going to continue to investigate with the laser measurement products that we provided to them. But the bottom line is, in a course of just about a half an hour, we started to troubleshoot the problem because we started to understand how the laser was performing, okay? I'm getting a question that says, how is ellipticity or circularity measured? Very good question. It is when you've got a scanning slip profiler or a camera-based beam profiler or even the Rayleigh scattering profile, what is measured is the major axis versus the minor axis, and the ratio between those two. So the major axis is going to be the largest width diameter. The minor axis is going to be the smallest width diameter. They're going to be perpendicular to each other. The ratio of those two is the ellipticity or the circularity measurement. So hopefully that answered that question. Case number 3, finally, is a laser metal cutting process. Okay, so you see a picture there. It's cutting very thick piece of material there. So what was happening in the troubleshooting of this particular system is that they were doing a normal run. They were applying the application parameters that were developed. into this system. They were doing a normal run, and what was happening is the cut was starting off good. We're getting really good penetration, just like you're supposed to. But over the course of this particular cut, the cut was declining. So you're getting a lot more dross, a lot less penetration. And then by the end of the cut of this particular piece, there was a lot of dross, there were a lot of sparks. There was actually no penetration at the end of the cut. So something was going on with the laser system. Run number 2, they just tried, they just wanted to try something, so they adjusted the position of the focus spot. So they raised they raised up the laser system just a little bit. At the start of the cut, there was no or little penetration. It just wasn't. It just was not reacting like it was supposed to. Very inconsistent cut at the very end. There was a lot of time spent troubleshooting the problem. There was a loss of money again in scrap material and a loss of labor money. So bottom line is they were not measuring their laser parameters, and this was the result. So we came in and we did a laser measurement technique. We took a water-cooled power sensor with a meter, so it gave a dynamic measurement. So when the laser turned on, you have a power. Several seconds later, you've got a second power. So it's a dynamic measurement of the laser. And then we also used the device that uses Rayleigh scattering to show the focus spot location measurement, okay? So it was giving a real-time visualization and measurement of the focus spot location. Well, what they found, and again, when we're talking about material processing, we're talking about the watts per centimeter squared. The power output was, by all indications, very good, so that part of the equation was not changing. What was changing was the location of the focus spot. There ended up being about a 7-millimeter drift in the focus spot location over a time period of about 4 seconds. So the cut would start off good, but because of this shift, think about it, the size of the beam that's being applied to the material is changing. So that's why they were seeing a very inconsistent cut. It was because of the change of this focus spot location. They started to troubleshoot the laser system, and they found out that one of the delivery mirrors was not being cooled, okay? So that was causing a thermal effect on the overall laser system. That was causing the shift of the focus spot over time. Okay, so in summary, there are many challenges that come with laser material processing. And to be honest with you, understanding how your laser is performing should not be one of your problems, all right? There are so many different products, modern day techniques of collecting information of your dynamic changes on your laser system out there that this really should not be a problem, understanding your laser and understanding how to manage those parameters. Good laser sources don't always translate into good laser processes. Again, laser sources, there are a lot of high-quality systems being provided. That it doesn't necessarily mean that the overall laser system is going to be a good laser system if you are getting, even if you are getting a good laser source. Good laser processes should be benchmarked and then maintained over time, realizing that, again, the laser is made of stuff. It will change over time. So benchmarking your laser process when it is good is really going to give you the best results in a successful laser process. In the event that you have to troubleshoot your laser, in the event that your laser does degrade over time. And then finally, laser performance measurement techniques have really evolved over the years. Please take advantage of these technological advancements because it really is going to give you a more thorough and a more comprehensive analysis and way of measuring your dynamic measurements over time. Dynamic measurement compared to the older legacy technology is really going to tell you the complete story of how your laser is performing over time. Again, that's me. I want to thank you for joining us today. I really do appreciate it. Please, if you feel free to reach out to me privately if you do have some questions. I've got a number of ways you can get a hold of me, email or LinkedIn. Those are probably the best ways to get out of me. Hopefully you're walking away with something that you can start to apply to your everyday laser life. So With that, I'm going to turn it back up over to John L. With any questions that there might be. I'm sorry, John L. You wanted me to answer the question, so I'll answer that. We do have a few questions here. How's the lipticity measured? I think we've measured that. Was the modified laser 2 still cracking welds? And this goes back to one of the case studies about how we made some changes. My understanding to the answer to this question is that they were eventually able to get to a place to where they were producing good welds for their laser number 2, and this is because they purchased and they started to apply the laser measurement techniques, and they started to better and more fully understand how their laser was performing. So they were able to characterize the application on the laser 1 when they had a good parameter or good set of parameters, and then take that and apply it to laser number 2 and start to see how the laser was performing with these better sets of parameters. So hopefully that answered that question. Looking down here, thank you. So ellipticity, circularity are the same even though they sound like opposite definitions. Ratio equals 1 is perfect. That's correct. So the ratio, so a 100% measurement of circularity and ellipticity, those are effectively the two very common terms. They effectively mean the same thing. Ratio equals 1 is a perfectly round beam. Yes, you are correct by that. So anything less than 1 is going to tell you how round or how circular your beam is. Okay. A couple of other questions here. One says, what can cause the changes in laser power or the beam size over time? Really good question. Again, it's really tough to nail it down to one specific component or set of components, but basically, again, the laser is made up of stuff. It's made up of things that are going to degrade. So anytime you get into maintaining a laser, you've got the potential of getting some component dirty, even though you don't intend on doing that. Anybody who's worked on a laser source, specifically ND YAG lasers, knows that if you have a lamp blow up, that's really bad. You get a lot of water and glass everywhere, and that's happened to me before. And I tell you, that is not fun, and it's not very easy to recover from. So you can do your best on maintaining and bringing that laser back up to snuff, but chances are, there's going to be a spot of water on one of the optics, and that's changed that laser system forever until you decide to change that optic. So really, any changes in any components, and by component I mean anything that's going to touch the laser at any time, those are really what's going to change the laser characteristics. So hopefully that answers that question. Let's see, looking down here, what will the beam measurements do when something is wrong with the laser? I guess probably the best way to answer this question is you want to, number one, take laser measurements, a dynamic laser measurement periodically to see how your laser is trending. Okay, and by trending I mean from the time you turn it on to several minutes or after the laser is turned off. Okay, so if you have let's just take laser power for instance. If you're measuring laser power, if you have a laser power that is X and it is X at the end of 2 minutes, then I'm going to say you've got a good laser source. I wouldn't change anything. I wouldn't worry about anything. But if you've got a laser source that you turn the laser on, it comes up to X, and then you start to see that graph or that number decrease, something is wrong with your laser, all right? I've seen cracked output couplers that cause this, bad optics that are just degraded to the point where they're just not effective anymore. I've seen powers that start off at X and then they bounce around, so they go up and down like crazy, and then they finally stabilize at a certain power. That particular laser source was losing resonator gas, so they found the leak, they repaired the leak, and they're off and running, and they've got a power Same thing with beam sizes. I mean, you're going to see the same thing in beam sizes. If you got a cracked alpha coupler, damaged optics, you're going to see a beam size that's X, and you're going to see it grow like crazy. So this is really where the laser measurement products come into play, is that it gives you a better understanding of how your laser is performing over time. Okay, let's see, I've got a couple of other questions. Is goodness a fit of better, is goodness of fit good, a good better metric than circularity? Boy, that's a really good question. Goodness of fit is a Gaussian measurement, and I would say that goodness of fit personally is not a better metric than circularity. They're just two very different characteristics of the beam. So you do want to have a nice circular beam, obviously, or as close as you can get to it. But goodness of fit is really going to be, I would say, a better laser quality measurement. So it's going to be more of a metric of what you should expect the laser to be. So obviously, if you are expecting a Gaussian type profile, the goodness of fit is going to tell you how close it is to that perfect Gaussian fit, and therefore it's going to be a laser quality, a laser source quality measurement, where the circularity is going to be more of a laser system quality measurement. And hopefully that answers that question. We're getting some really good questions. I've got about 10 minutes here. I'll do my best to answer them. How often should we be taking laser measurements of our system? Very, very good question. Really, honestly, that comes down to you. There are a lot of different factors that play into how often you take measurements. Me, personally, I've never owned a laser system, but if it were me, I would, number one, take measurements at your system runoff. You are paying a lot of money for this laser system. You should look into investing in laser measurement products early into the in the life cycle of that particular laser system. Take measurements at system runoff. Take measurements after the delivery of the system to make sure nothing has changed. And then at that point, take measurements frequently just to make sure you do not have a laser process is changing. And then once you've established that baseline, you can kind of come off of it. Once you know that your laser system is performing like it should be, once a month, once a quarter. I've got automotive people who measure once a shift. So it really does come down to your own personal preference. But hopefully you walk away from this with some good recommendations. Okay, another question. What is the biggest barrier you've seen from customers who should be benchmarking a process but ultimately don't? Equipment cost, skill set, personnel. And my answer to this is yes. All of these are barriers. Beam profiling especially is something that, for whatever reason, is just not very well understood. It's my fault, that's our fault for not doing a very good job explaining how simple it is to take a beam profile and how effective it is. So there is some timidity there, right? So there's, you get kind of nervous about buying beam profiling, thinking, I'm not going to be able to apply this data. Hopefully this webinar has changed your mind about that. Skill set. When it comes to skill set, we as a company, we really pride ourselves on service after the sale. So you should find a equipment supplier that's going to be there to train you when you don't understand what measurements you're getting to increase that skill set. Personnel, that's another thing. Another thing that I might add to that question is your operating environment. So some companies, very resistant to change. They don't want to know this information. Get out of here. Ignorance is bliss. Let us continue to do what we want to. Ultimately, they are going to run into problems with their laser system if they don't measure. It's going to happen. So hopefully that answers that question. And then finally, the last question I'm getting, what laser source or system is recommended to cut thin polymer materials with high quality, smooth edge, no beading, no thermal damage? I'm going to decline on that answer, to be honest with you. I really wish I could very effectively answered that question, but I'm not publicly going to recommend a laser system manufacturer over another. I'm sorry. I'll decline on that answer. So those are really all the questions. Again, very good questions. Hopefully, I'm leaving you with something that you're going to walk away with and apply. But Jonelle, I think we're done. Unless there's something else.
Excellent, John. Great job. Lots of good questions. I just want to take a minute to thank you, John, for the presentation today. You did a great job. We also want to thank Ofer Spiricon for making today's presentation possible. I want to let our audience know that the presentation will be archived within 24 hours, and you can access it from our homepage at www.industrial-lasers.com. We will send an email message out to all the registrants with a direct link to that archive, so you can look for that. Again, thank you, John. We appreciate you sharing the knowledge with all of our viewers today, and we thank our viewers for taking the time out of their busy schedules to join us today, and we look forward to future webcasts. Have a great day, everyone.